Hello, let's do a review of section section 5.1 and 5.2 of Math 125. So here it is. In 5.1, we start talking about integration. And how do we start with that? We first talk about how we're interested in finding the area if a function f of x is bigger than 0 on a closed interval a and b. We're interested in finding the area underneath the graph of the function and above the x-axis between a and b. Here's a and b, point a and b. And so this is, let's say we know a few shapes that we can find the area of, but not necessarily any curve that you give me. I can find the area underneath it at this point. And so what happens is that the first thing that we know is the easiest area I can find is area of a rectangle. So why not break down under the area underneath into small rectangles and compute the area of those, approximate the area underneath by finding the sum of those rectangles. And so the first step that we take is that we divide the interval a and b into n many little pieces. And it's a nice practice to have these n many pieces of the same size and basically build little rectangles on top of them. So n many pieces, b minus a over n, and you get these little piece, and then basically by picking a sample point within each interval and finding the value of f of x on that sample point, you can find the height of the rectangle or length of the rectangle, and then find the area of the rectangle by multiplying little delta x by that f of that sample point, and another one for the next one and another one for the last one. So the area is going to be approximated by the sum of these. And then notation wise, this is how we denote the area. It's the elongated sum from a to b of f of x dx, and that is according to what we discussed as can be approximated by the sum I equal to 1 to n of f of xi delta x. And then if I use many little rectangles and make the width smaller and smaller, this sum gets closer and closer to that area that we denoted by definite integral, and we call this definite integral. So basically this is explaining, because if n grows, the approximation gets better and better, so the definite integral is equal to limit of that sum basically. And so one important part of the mathematics is now the next part that we want to discuss is from sections 5.3 and 5.4. In 5.2, this is 5.1, and in 5.1 2 and 3, we sort of discuss definite integral. And so what is a definite integral? Definite integral f of x dx f of x dx is antiderivative of f. So it's f of x. There are many of these basically, and they are all different in a constant. And if I take derivative of f prime, f, the capital F, I'm going to get the small f of x, basically. That's what antiderivative is. And so the Riemann sums are fun. That's the integral from a to b. That's the definite integral. And this is the indefinite integral. And you guys wonder why these two have the same name, and the reason is that you actually can use the antiderivatives to find the definite integrals. And that is for you the basically fundamental theorem of calculus part 1. And so what does it say? It says if f is continuous on a and b closed, a and b, then you can basically use that antiderivative. So the integral from a to b of f of x dx can be computed by plugging in b into the antiderivative and then subtracting a into the plugged in into the antiderivative. That is f of b minus f of a. So, and then we kind of figure out in just in a few minutes after we discuss the fundamental theorem of calculus that actually not only continuous function on in closed interval a and b would work, but if you have finite number of jump discontinuity, or if you have a few holes in there, it's okay too. And then we say, well, in calculus 2, there a little bit more than could be okay, basically. And so that's another discussion that we will have on the calculus 2 part of this integration, basically, which is not related to fundamental theorem of calculus, but basically a new definition if you have infinite discontinuities. And so that said, all of these discussions that we had, we are talking about f being a function that is the output is always positive. What if f sometimes is, if there is an f such that f is sometimes positive and f sometimes is negative? What do we do with that? Then in that case, basically you will have if you compute the Riemann sums, you will figure out that Riemann sum is approximating area underneath in the positive side minus the area above in the negative side, between the function and the x-axis. And so it's always the net area. If you want to find the total area entrapped between the function and x-axis between a and b, then you have to basically find the definite integral of not f of x, but absolute value of f of x dx, basically. And so this said, there are a bunch of nice properties that a definite integral have, and so we discuss that next and give you a few examples.